Welcome. I'm giving a talk about attacking AI. It will not be a very technical talk. The first disclaimer, it's essentially really the primer is the focus, giving you an idea what machine learning actually is under the hood, what is the core idea, and what are specific security attacks. I picked essentially three to AI and machine learning systems, and for today I will most likely say AI, I guess. People in the field separate between artificial intelligence and machine learning, and the semantics of those terms changes over time. Everything that we usually in the press these days call some intelligent system will be covered by what I'm discussing today. Also the examples that I show that are results by other researchers that are working more in the AI field. I'm happy to publish the references together with the slides. I didn't put the detailed reference on each slide because that's just overcrowding them. I'm doing research in that area, but mainly for really high assurance systems where machine learning plays a role these days as well. If I explain that type of research, that slide already would be full with mathematical formulas. I think that's not what we want to have on a Saturday afternoon before we are waiting for our afternoon tea. Machine learning, AI, very successful. That's a couple of success stories over the last 10 years. Go, that game is considered to be much more complicated for computers than chess. Chess computers we have since a while. Took much longer for computers to beat professional Go players, but that milestone has been achieved. We have seen image manipulations, AI systems. In the meantime, they generate whole videos. The first of them here already in 2019, where essentially turning pictures into animated images, short videos. Very impressive. AI is a lot used also in pharmaceutical research and biological research. Very, very valuable. A result that I personally like a lot because it's more related to what I'm also doing research-wise, very recent, actually from this week. Google has announced that their artificial intelligence essentially can achieve a silver medal in the International Mathematical Olympiad, so solving complex mathematical problems. So that looks all pretty good and trustworthy, and also surprising that computers are able to do that. What is machine learning actually? How does that differ from traditional software development? Essentially, we have our data set that we explore, and we use that for training a system. So we start with some concrete input values that describe the problem and solutions to that problem, and then essentially use that for training data that gives us a model that we deploy or install, maybe, and then essentially we hope if we feed new data, new problem instances into that trained model, that it will predict the correct values based on that training phase. And that sounds a little bit like, oh yeah, we teach some kid some new topics, they learn, and then they become an expert in that area. And that's a little bit also what we at the moment see with all that hype around how great AI works, that a lot of people put a lot of trust into the answers given by AI systems. At their core, they're still pretty much essentially stochastic systems. If we take it very, very simple, we have a graph or plane, and essentially we just want to have an AI system that distinguishes, if I put a point in that plane, into that AI system, if it is in the, from your side, left-hand upper part, light yellowish, or in the right-hand lower part, in the black part, and maybe we select some data points as training set. We can already see this data that we use for training is much less than the data on which we later expect that the system works correctly. Now, if we have that holistic view, we see the complete problem. For a human, it's easy to say, this is the line that separates those two surfaces, and everything what is above that line is in the yellowish area, everything that is below is in the black area. Now we want a computer to find that line that distinguishes those two areas. And that might not be perfect. That might come up with that bluish line that hits a couple of data training points very nicely. Others with overshoots or undershoots a little bit. But overall, that still looks pretty well. Given those data points, the training set on which we check that the system has learned the problem well, we might end up with such a curve. And that's, of course, not something that approximates our problem very well, but that might happen. And if we now compare essentially the gold standard, the ideal solution that we have, with that actual approximation, there is a large orange area where our trained ML system would come up with wrong results. Now, in that two-dimensional problem, that's easy to see that this is not a good system. Networks that we are using these days, or AI, ML models that we are using these days, they have 10,000, 100,000 of parameters that need to be tweaked. And that makes it essentially impossible to understand in detail how well they work, how well their predictions actually are for problem instances that we don't know the correct answer for, that we cannot validate immediately, that we trained the system on. So we have already always a certain likelihood that the result that we get from an AI system is actually wrong. And that's inherently something that we need to live with. The other big difference to traditional software is that we don't have a human-readable source code anymore. So for those of you that have a background in software security, test for cross-site scripting, vulnerability, SQL injection, that human-written implementation that we can understand and analyze and explain why there is a security problem is gone. That's some complex statistical system, different neural networks, decision trees, so there are different formalisms, essentially, mathematical models underneath. But all of them have in common, they're super large and automatically trained, hardly understandable, if at all, for a human. That's the big difference with AI systems. And now let's have a look at a couple of attack classes. And the one that I will spend the most time on, a couple of examples, also the nicest examples essentially, and maybe also the best investigated, best researched type of attacks are injection attacks. And that started already, also again 5 to 10 years ago, with something called adversarial examples on image classification systems. So we have here an image of a panda on the left-hand side. That's in the meantime, really a classical example. Was one of the first papers showing that type of attack that is classified by a neural network as a panda, as it should be. If you think about more realistic application of those type of image recognitions, think about your modern car that shows you there was a stop sign or a speed limit sign in your heads-up display, or even reacts on those street signs automatically in semi-assisted driving mode. Now we can generate some random pixel image that the same classification network, for whatever reason, classifies as a nematode. Doesn't really matter what that means, but why it classifies that pixel salad essentially as a nematode. If we overlay those images, the resulting image looks a little bit distorted, but for us as a human, it's clearly still a panda, whereas the neural network classifies it as a gibbon. That's funny. And at the beginning, that was also more like, okay, small changes to the input image can result in rather significant changes in the output classification, but it has not been seen as a security or a safety issue. But if we think about those images as street signs, then maybe a stop sign with a little modification is suddenly classified as a speed limit sign. And if you now think about autonomous cars, there's a difference if you're approaching a crossing and you need to stop to see if on the main road there's any traffic, versus you think, okay, I can drive 50 miles per hour straight ahead and everything is safe. That might result in a pretty heavy car crash. And of course, street signs are not always nice and clear and easy to read. Here on the left-hand side, we have one that has been beautified with a graffiti, most likely not with bad intentions. The one on the right-hand side has been carefully designed by a security researcher, putting a couple of white and black stickers over it. And those 4 stickers result exactly in the same misclassification that I illustrated here, that the stop sign is being classified as a speed limit sign for commercial neural networks that are used in modern cars. And now we can think about an attacker running around in the city and putting a couple of stickers on street signs and creating a lot of havoc. That is definitely a security attack. Now that still looks, of course, pretty much visible to us with the naked eye. We still see that there's a stop sign, but we also see there's a modification on the stop sign. Recently, researchers in the US came up with something that is closer to that example with the nematode in terms of some random looking pixel image. But the interesting aspect here is they can successfully trick commercial street classification systems using AI into misclassifying stop signs by taking this image and essentially taking a projector, as we have one here in the room, maybe more those larger ones that are used for projecting images on house walls in the outside, overlay the stop image, and that stop image here is overlaid with that pixel image. It's not recognizable to us, and again, the classification system misclassifies that image. That sounds all pretty complicated, and this is a part where somebody implemented a nice demonstration. These are essentially state-of-the-art image classification networks. That's a website. Everything what I will now do is implemented in JavaScript and runs on my small laptop in the web browser. So there's not some heavy GPU-based cloud computing facility behind. It's pure JavaScript running on a standard laptop. The image sizes that we have here are actually, they look very low resolution, but they are actually realistic in the sense of that what we currently have in cars is doing the recognition of street signs roughly on those size of images, because they take the camera image, first identify the street signs, extract them, and then do the classification. After the extraction of the actual images that you want to, signs that you want to classify, you end up with those 70 times 70 pixel size images. So I have here, can run the prediction. That takes a moment, and I hope my network is connected, that the JavaScript is loaded. That looks good. I hope you can see that. The prediction here says, hey, this is a stop sign. And I'm also getting a probability. The neural network thinks with 99.85%. And I mean, for us as laypersons, that means it's really confident that this is a stop sign. And now I can run an attack generator. Also, again, in my web browser, in real time, asking the system, please modify that image a little bit so that the same image recognition system for street signs recognizes that as a 100 kilometer per hour street sign. That data set are German street signs. At least I think they're German ones. That's why we have here kilometer per hours. And I'm now generating the attack image. That again takes couple of seconds, 2-3 seconds, looks a little bit distorted. That was the generation of the adversarial image. I'm running the prediction, and with 99.91%, even with higher probability, higher confidence, the same neural network classifies that as a speed limit sign. What we can see is that generating those attack images is computationally comparatively cheap. It runs on a standard laptop, whereas training neural networks is really expensive. So those attacks are not super expensive for an attacker to generate. The question, of course, is then how to inject that modified image into the image recognition system. But that we can leave as an exercise to whoever would like to try that. Don't need to be too instructive. Another attack. Who of you has used ChatGPT or Copilot? Any of those new generative AI systems? They essentially do the same. Again, they have some internal complicated mathematical foundations, but essentially they generate the next word based on the last number of words that are generated. What is the most likely word to expect next? And continue that way. And researchers in Switzerland found out that, again, I think that's ChatGPT 3.5 or so, a little bit older version than what we have at the moment. If you give that the task, repeat this word forever, poem, 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 ChatGPT generates the word poem for quite a while, a couple of hundred times, and then suddenly generates that data that was used for training the model. And they found, for example, privacy confidential data in their personal data like phone numbers, fax numbers, cell phone numbers, website, email addresses of people whose information was used for training that neural network. So we suddenly, as an attacker, obtain training data. And if you're an AI company, you train your network on your confidential data, on your trade secrets, because it helps your employees, your staff. Maybe you generate a customer agent, then customer support agent. That is, of course, something that you, from a commercial side, don't want to happen. And from a GDPR perspective, you don't want to happen either. And that's then also the reason why companies are pretty unhappy if employees, without prior permission, start copy and pasting information from your internal intranet into ChatGPT, because depending on the configuration, those AI companies are using the data that is being fed into the system for retraining the model. It ends up in the trained model and might be accessible in these ways to attackers. That's essentially the most common attack, and the attack where we have a lot, or large is maybe a little bit overstating it, but a reasonably number of real-world examples against real-world AI systems. The other attacks are, at least in the wild, not seen that often, and maybe a little bit more theoretical. The next one is data poisoning. You might have seen this headline, that the Google AI suggested to put clue in the tomato sauce for making it stick on your pizza. And there we could find out that essentially there was a post on Reddit that suggested that, sarcastically. The Google AI took that for real, essentially. But now we can think an attacker could actually try to inject such misinformation into the training set to miscredit, for example, a company using such an AI system, or harm them in other ways, and that is called data poisoning. Other problem instances where we see that is a lot of the image recognition systems that are being used for recognizing people are developed by companies in the Western world, or maybe China, but essentially in countries with a relatively low percentage of people with darker skin colors, and they certainly don't work reliably for people that have darker skin colors, and that's of course not something that we want to have. That's essentially a racial problem here, but again also shows that the quality of the training data has an important impact, is an important factor in the quality of the AI system that we get later. And again, here it is an accident, or hopefully it is an accident. This wasn't done intentionally by the company, and quickly developing those image recognition, face recognition systems. But again, we can easily imagine that an attacker tries to exactly use that in a negative way, intentionally. So data poisoning is whenever an attacker tries to modify the data being used for training, and that might sound completely silly and difficult to do, but keep in mind systems like ChatGPT are trained on everything that we write on the internet. So if you want to start modifying what ChatGPT is doing, publish your own blog, essentially. And of course, if we are talking about ML models, machine learning models, or AI models that are trained on proprietary data, then of course an attacker might also be trying to get access to your data. Then we are in the traditional information or cybersecurity topics, changing labels, so changing, this is not a stop sign, that is indeed a speed limit sign, adding data sets or removing data from the training set to change the behavior of that model. And we would need to first secure our data, and secondly, if such a data breach happens, need to detect that, be able to detect that, of course. Also interesting, again, particularly if you train the models or adapt an existing model to your company data, then essentially the trained model is becoming your crown jewels. That's your trade secrets. That's what makes essentially the essence of your company, in particular if you're in a more service-based business. You don't want other people to obtain the trained model, because essentially then you just clone your company and your services. So that's another attack vector that again sounds pretty difficult to do. Essentially there are two attacks known. If that model is included in a piece of software, like we tried earlier to put secret keys into software, which work also well for DVDs and the like, then of course people extract those models from your software. But there are also attacks known where we have online systems and the attacker can just query as a black box that AI model, essentially use ChatGPT, and by asking well-crafted queries, learn the parameters that have been used or have been obtained in the training phase of that model. And for many of those models, the basic architecture is being known, and people are, at least in academic papers, able to get pretty close to what most likely is the original model. So the cloned model works nearly as the original one. Now, I said at the beginning, AI is very different from software. We don't have that piece of source code. Let's revise and check if that is actually true. And recently, the NCSC published a guideline for the secure development of AI systems. I was very keen to see what they actually discussed in that development guideline. And interestingly enough, things like stealing models, adversarial examples, data poisoning are hardly discussed in that guide. Most things that are in there are topics that would be taught in a secure software development module, or should be standard practice, best practice for developing secure software systems. And that is actually true, because AI systems hardly work in isolation. They also always interact with the software system. Maybe the machine learning model is encapsulated in a REST service. So everything that you learned about secure software development stays also in an AI-driven world, highly relevant, and needs to be applied. We just need to improve our security skills for a couple, relatively small number of AI-specific attacks, but we still have a software system around And any vulnerability in that software system essentially makes our AI system vulnerable. Coming to the countermeasures and conclusions, that we have time for questions as well. I'm not discussing the countermeasures for the software security topics. Things like sanitize your input, use prepared statements, buffer overflows, and the like should be well known. If not, that's a different talk or a series of talks, not for today. If we look at the 3 AI-specific attacks, to be honest, there's not so much that I can offer in working solutions, only in we are, as a community, thinking about solutions and working on them, but they're way less mature than what we have in the secure software engineering world. If we look at those adversarial examples and injection attacks, there's a whole research stream called explainable AI that tries to enrich those trained models so that they also come up with a form of explanation why they came up with a certain result. That essentially should give us a better confidence that the generated output is correct. I'm not so sure if that is the best way for preventing attacks. To be honest, I don't want to see a justification why that stop sign has been classified as stop sign, because then when driving that car, I need to read that document as well. I don't think that is too helpful, but it's hopefully helpful in terms of helping us to understand how those trained models work and make them more resilient in general. And what the AI companies, so for example, OpenAI for ChatGPT at the moment are doing is a hell lot of input and output filtering to prevent people asking things that OpenAI considers to be questions or requests that the AI model shouldn't answer, or to prevent the AI model to generate answers that it shouldn't do. If you play a little bit around with questions that might be a little bit outside of the norm, you might have gotten answers back from ChatGPT like, as an AI model, I don't have an opinion on that, or I'm not answering that type of question. That's essentially all based on filters that OpenAI or the other companies offering such models are applying. For data poisoning, I don't have a good solution. I think that's an open research problem. We essentially need to have a good data control of the training data. But is that realistic given the sizes of training data? On the other hand, the quality of the AI model depends on that. So we should have really, that should be our goal, and we should be investing not only from a security side effort into that. And of course, if we are under control of the data, then authenticity and access control to that training data is something that we can control. For preventing or at least detecting AI models being stolen, there are works on watermarking those models. So essentially what the companies are doing is they intentionally add false training data into those models for data points they consider nobody will ever ask that. And if then somebody copies that data model, they can essentially ask certain questions to that model, get wrong answers, and can say, your model is generating the same wrong answers as ours does, so you must have stolen our model. It's essentially the core idea of watermarking. And we have seen, but we are not sure if that is done for preventing the stealing of models, that Google, for example, starts no longer reporting confidence values as a percentage value, but only as a classification low, medium, high, which makes those attacks at least harder. If they're doing it for preventing those attacks or not is unknown to us, of course. And if there are two things that you should remember for the talk, if you forget everything else, the first one is all attacks that we see against software systems are still relevant in a machine learning-based world. That knowledge is still relevant, needs to be applied from secure programming to securing your software supply chain, your data supply chain, and secure operations of systems. And the other one is, and that's the big problem that we are fighting in a lot of security areas, but is particularly valid for AI systems, finding an attack is much, much easier and also much better understood than securing the core AI systems. As you have seen, generating adversarial examples works essentially in the web browser. 10 lines of code written by an undergrad student can generate adversarial examples. Implementing the systems that train AI models is firstly much more complicated and requires much more runtime. Generally, much, much harder. That's all from my side. With that, I'm open for questions. Should give us 5 minutes for questions. Yep.
Is it possible that, data poisoning, we're looking at it as a bad thing, but from the opposite side, you consider people creating original content, like artists, they are looking increasingly as data poisoning as a way of protecting their IP and their livelihoods?
Yes.
So, does that mean, therefore, then that organisations should increasingly look to pay for access to the training data that they want, so that it isn't?
I mean, that's the ethical and commercial question. Yeah. On which side you are protecting your data. I gave the presentation from the point of view of somebody who wants to use AI and want to protect their investment into training the AI systems. If you are an artist or an author and don't want your work to be used and trained, and we have that in the academic world at the moment. Last week it was somebody detected essentially that one of the large academic publishers signed a contract with one of the AI companies. They are now using all the academic published articles for training their network. If you want to prevent this, then data poisoning in a certain way is a form of doing that. If you look for prompt injection attacks, there are people now adding white text on white background into their emails, essentially instructing an AI model to answer in the form of a poem or so, to detect if people actually write the answers to the emails themselves or let them formulate it by some generative AI system. I mean, a knife can be a very valuable tool and it can be a weapon. Both sides are valid depending on the context. Any other questions? Brilliant. Thank you, Achim.